Howdy, howdy. We're going to be talking about matter today. Before we can get into chemistry in detail, we have to have some sense of what we are doing and what we're talking about. And as it turns out, chemistry is the study of matter and the changes that that matter goes through. So we have to come to terms with the properties of matter and how we classify matter, and that's kind of what this introductory stuff is all about. Well, you probably heard some of these things before, or at least are aware of them. Obviously, matter is the stuff that the universe is made of, and one of the most important properties then of this matter is that it has mass. Mass is a measure of the amount of substance. The fundamental building blocks of matter are atoms, although you probably know that it's possible to split atoms. As it turns out, if we do that, subatomic particles have very, very, very different properties and tend to be relatively short-lived in terms of their existence, and as a result, atoms become for us essentially the bottom line, as it were, and elements are going to then be composed of these atoms, and that compounds are going to be composed of atoms that are chemically bonded together. Nature favors low system energy. I'll say it 4 million times probably in the duration of this course, and it's such an important big idea that I don't mind saying it a lot. As a result, we see in nature that mostly our elements, which are on that periodic table, are not found all by themselves, but rather found in compounds. And these compounds then are numerous, millions and millions of different combinations of those elements. And so we spend a lot of our time, most of our time really in chemistry, talking about compounds, their properties, and how they interact as opposed to those elements. But it's important to see that those elements are the building blocks. Well, how do we know about things? We know about things based on the properties that those things exhibit. Properties are things we can measure. And so we think about properties and we quickly come to a realization that there are really two fundamentally different kinds of properties. One of those properties is said to be intensive and other sets of properties extensive. The difference here is that intensive properties are perhaps what we might call fundamental in that they don't depend on how much substance you have. Some of these properties that are important that we'll talk more about later are density and the various physical melting and boiling points that substances have. A careful view of the periodic table will list a number of these intensive physical properties, and they're critical because those properties allow us to uniquely identify a substance. Whereas extensive properties are those that are, if you want to think of them that way, rather trivial in the sense that they depend on how much mass the substance has, and that would resolve itself in a variety of different things. Mass itself is an extensive physical property, as is shape, size, and a variety of other properties that we can measure but don't really help us in terms of the identity of a substance. To say that you have 150 grams of a substance gets us no further down the road in terms of its identification, but to say you have a substance with a density of 1.5 grams per milliliter does in fact give us some useful information and helps us identify that substance. So we'll be going back and forth talking about intensive and extensive properties. We'll do a lab soon with an exploration of these various properties and thinking about how that takes place. Another important distinction between physical properties and chemical properties of substances. The easiest way to explain the difference is to think about the process of measurement. And if you can measure some property without changing that property, then what you're measuring is a physical property. Size, then mass, weight, any of those things are physical properties because they can be measured without changing them. Chemical properties are different. They cannot really be observed without exploiting them. That is to say, think about the chemical property of flammability. Although you can probably predict with some certainty what substances are going to be flammable or not, that's because of your long experience in the world. But if you think about it something like a piece of paper, there's absolutely no way that we can establish whether or not it is flammable, whether it has that chemical property, unless we try and light it on fire. And the interesting thing is, if we discover that it is flammable, flammable, once the paper has burned, it is no longer flammable. And so the chemical property is lost as the chemical property is revealed in kind of a weird way, huh? So chemical properties then become very, very important because they're the ones that are going to determine how different substances interact. And we'll have a lot more to say about the difference between physical change and chemical change and the evidence for that chemical change. So how do we classify matter? Very, very simply, we start with categories that relate to the substance and whether it can be separated by physical means. If you think about some sort of salad as an example, where you could easily go in with a pair of tweezers and separate the different components of the salad into separate piles by physical means, and hence a mixture, right? If you can't separate a substance by physical means, then we've got a compound, a pure substance, and those pure substances then are obviously very, very important to us in chemistry because those pure substances all have certain attributes, certain intensive physical properties that allow us then to characterize them in a very, very different way than mixtures, which are physical combinations of ingredients but can be separated by physical means. Another interesting example of a mixture would be salt water. You probably all know that if we put salt in water, it dissolves. And you might think that that is some kind of chemical change, but it's also interesting to realize that if you take that salt water and allow the water to evaporate, a physical change, the salt will crystallize in the bottom of the container, and hence suggestion that the dissolving of salt was a physical change simply because we could extract it by physical means. Not only that, it suggests that salt water is a mixture rather than a pure substance. In terms of our mixtures, we ask one question and we're essentially done. Is the composition uniform? That is to say, are all samples the same? If the answer to that question is no, then we end up with something called a heterogeneous mixture, and quite frankly, we're not going to deal with too many heterogeneous mixtures in chemistry because they're very difficult to characterize because the mixture is not homogeneous and is not uniform composition, and as a result, we can't really deal too well with it. We will have quite a bit to do with homogeneous solutions, those that have a uniform composition, because those homogeneous solutions take a variety of important forms in chemistry, perhaps most notably solutions like salt water that we're going to use an awful lot in chemistry. And so those mixtures will be important to us, but mostly the heterogeneous mixtures are ignored. The homogeneous mixtures are the ones that we deal with later in the course, really, when we understand how simpler states of matter behave. Again, you're going to do lab here, and so a lot of this you'll see rather than just hear me yak about. In mixtures, the substances retain all of their physical properties and obviously can be separated using those physical properties. Another good example is if we were to mix iron with some other non-metallic element and then we took a magnet and trolled it through that mixture, we could easily extract the iron from the mixture by virtue of its physical property, magnetism, and that's a good example of a mixture. You'll do a lab where in fact you do that very thing. Pure substances then consist of elements and compounds. And the key question here is whether or not that this pure substance can be decomposed further by chemical means. Now, remember, physical means separate our mixtures from our pure substances. And here we're asking the question in those pure substances, can we decompose them by chemical means? If the answer is no, that it can no longer be decomposed, then what you're dealing with is one of those 100 or so naturally occurring elements that are on that periodic table. And that's as far as we can go in terms of ordinary chemical means. As I've mentioned before, we can certainly split atoms, but when we do so, we end up with a bunch of particles that no longer have anywhere near the properties that the atoms have, and so we're going to stick with this idea of can it be decomposed by ordinary chemical means, and if the answer is no, we end up with an element. That is to say, picture a chunk of lead, and there's nothing that we can do to that lead chemically to decompose it any further. It will always be that element. If we can decompose by chemical means, then what you're dealing with is a compound. And a compound is, in fact, a pure substance, and it is formed as a result of the chemical combination of elements. Elements compose compounds, and compounds really are the bread and butter of chemistry. Millions and millions of known compounds from those 100 or so naturally occurring elements, and we spend most of our time in chemistry talking about those compounds and their properties as opposed to pure elements. What is a pure substance then? The two properties that it must have are that every sample of that substance must be the same, it must be uniform in its composition, and it must have a definite composition. And as we're going to see, the way that we represent that definite composition is with a chemical formula. Compounds obviously have different properties than the elements that they contain, and this is a fundamental and critical concept, right? We're going to often take elements and combine them to make compounds with very, very, very different properties. And then the last element there, then our last bullet point there, simply my point about the lead. The periodic table then, which you can find many out there, and I'll show you one in just a minute, is our fundamental building block. Contains information about the elements, and the elements are arranged in a particular fashion that makes a lot of sense once you know how to decode it. The symbols are very important. If you look at a periodic table, and you should do so right after you're done looking at this, or perhaps we can look at the one I'll have, you'll see that symbols consist of one or two letters. The first one is always capitalized. The second one never is. And those two letters must be rendered in that fashion for unambiguous communication between chemists. Notice that there are both rows and columns. There are 7 rows and there are 18 columns in that periodic table, and a lot to be said about the significance of those rows and columns. The rows often called periods, hence the term periodic table. The columns, groups or families, and as we're going to see, those columns are critical in establishing the chemical reactivity and identity of the various elements. Again, scanning that table, you'll see, interestingly enough, that most of the elements are metals. In fact, the entire left-hand side of the chart consists of metals with metallic properties, and we'll say more about metallic properties when the time comes. On the right-hand side of the chart, we have mostly nonmetals. We have all nonmetals, and many of them are gases at room temperature. Now, we'll have, not surprisingly, a lot more to say about phase, too, later, but for now, we'll just note that many of those nonmetallic elements are gases. We also have a transition zone that cuts across the right-hand side of that periodic table in sort of a stair-step fashion, where the properties change from metallic to nonmetallic. And this blending of properties produces a handful of metalloids, which are distinctive elements that we'll have a little bit more to say about later. Here's an example of a periodic table. I don't know whether you can see it as well as you might be able to, but it does show the various points. Here is that stair-step line that separates the metals from the nonmetals, and boxes touching that line, typically then referred to as or metalloids. Here then the whole left-hand side of the table, the elements that are metallic, the symbols represented, again, some of them 2 letters, some of them 1 letter, some history there, but probably we don't need to go into it. And in this instance, the elements have also been keyed in terms of the color, in terms of the group that they belong to. We're going to talk more about the active metals over here, the transition metals. The post-transition metals, they're the non-metallic elements, and the special noble gases there. But for now, we can just sort of recognize the general shape of the table. Students always wonder about the 2 rows down at the bottom of that periodic table. Typically, those are shown down there for convenience sake. They actually fit up in the body of the table if you follow the numbers, and we'll have lots more to say about the numbers there. You see that they actually fit in right here, but if we put them in there, the table gets very, very long, and it's simply easier for us to show them below. Sometimes these are referred to as the rare earth elements, and we'll have, again, more to say about their specific nature later. Notice of those rare earth elements, only uranium and plutonium are familiar probably to you, although we're seeing increasingly that these rare earth elements are very important in the new green energy technology, and so perhaps we'll hear more and more about them in the years to come. Notice that the numbers go up to about 109. The exact number of elements, I don't even know anymore, but since we can synthesize them under various circumstances, but for our purposes, we just refer to the 100 or so naturally occurring elements, and as we're going to see, the bulk of your world is made up of very few of these 100 or so elements, and so we'll see a number of elements very, very common, and others we won't run into hardly at all. It's worth a little time to look at the periodic table and familiarize yourself with it and begin to sort of see common elements. Many students are drawn to the central core of the transition metals where their old friends gold and platinum and silver and copper are. And as addition to that, the elements over in the right-hand side that are gases at room temperature, in particular nitrogen, oxygen, sulfur, a fairly common element in people's experience, and so we'll have a lot more to say about them. Elements then, the fundamental building block of matter, and compounds made from those elements, and we'll begin to explore how those come together to make chemistry.